see, have been keeping up a design reference architecture to serve as a benchmark of how we might explore Mars. It is not necessarily the way in which we will explore the planet. We use it to compare and contrast different ideas, new approaches, so that we have a common reference to assess different technologies and system concepts. So we're constantly updating it as we go along. We had the latest version is what we call Design Reference Architecture 5.0. It was a body of work that was finished in the 2007 timeframe, and it was published in 2009, formally documented in 2009. We're currently starting the next process of updating that. So we'll go through another approach to compare and contrast different approaches. And when that body of work is done, we will update the design reference architecture. So again, it's used to help frame some of the discussions, used as kind of just a common reference to compare and contrast different approaches. In order to help frame some of the discussions, you need to understand human round-trip missions are a little bit to Mars are a little bit different than what we typically think of for space station or what we had with Apollo. In those missions, the Earth was the central body, and the Moon, space station, orbit Earth. And so, you know, from a broad perspective, you can come and go to and from those destinations almost any time within certain constraints, almost any time you want to. So if the problem arises, you have the opportunity to come home. For Mars missions, the Sun is the central body. Both Earth and Mars are orbiting the Sun. And so it's important to understand, and you design the mission, you have to plan the mission, not only the outbound trip to rendezvous with the planet, but you have to keep in mind where Earth will be on the return trip. And the relative phasing of Earth and Mars and the trajectories force you into two general classes of trajectories. Over on the right, you see what we commonly refer to as the short stay type of mission approach. That's sometimes called an opposition type class mission. And you can see the mission profile in that is generally characterized by one long transit out to the planet and one short transit. We generally try to shape the mission so we have a short transit out to Mars so that the crew is less deconditioned, get those transits down to about 180 days or so. But when they get to Mars in this fast transit out, Earth is in the wrong location to come home, and every day you stay on the planet, it gets worse. So there's a general tendency to try to get to the surface, explore as quickly as you can, and then start that transit back. And generally the transit back involves a Venus swing by. Pick up a Venus swing by to help you with the trajectory, to help reduce the velocity requirements. The other approach shown on the left, is on the right, is what we call the long stay mission, or commonly referred to as a conjunction class mission. In that mission, you dash out to Mars, and when you get there, instead of staying a short time and then chasing Earth back, you decide to stay for a long period of time. Stay up to about 500 days exploring the planet, waiting for that proper alignment of Earth and Mars so that you can dash back home again. So generally, the velocity requirements, which is very important to us from a mission planning perspective, because that drives the launch vehicles, drives the propulsion systems, is very important to understand and try to minimize those as much as you can. And with the left-hand side short stay type mission, there's a large variation in the amount of energy required to conduct that mission. Whereas the conjunction class mission are fairly stable, and they're less required in terms of the total velocity required, which is important, and Ben will talk a little bit more about that in the transportation section. But from a human health and risk perspective, it's also important when you understand those mission classes to understand the total trip time associated with them. And you can see over there on the left, the opposition class, which is the short stay mission. You can see the bars associated with the outbound trip, the time that you spend there, and the return trip. The mission durations are on the order of about 18 to 22 months total mission duration. And you're only spending 30, 60 days at the planet. So most of your time is spent in free space, the radiation environment, which Charlie Golden just talked about, zero-G gravity environment, traveling out to the planet and back. And only 5% or so of your time is spent at the planet in a gravity environment. Conversely, the long stay mission, you dash out to the planet, but you spend about 500 days on the surface and then dash back in about another 180 days. So each one of those transit legs on the long stay mission is essentially what we demonstrate every time we send a crew to space station. Crew rotation to space station is 180 days. Each one of those transit legs on the long stay is equal to that. So it's very important from a human health perspective, from a total system reliability perspective, and maintenance of systems. The mission durations are important, and you see that they're, from a general perspective, they're the same. Long missions, regardless of those mission approach you have, they're still long missions. They're on the order of 18 to 30 months long. So those can serve some significant challenges in terms of the overall exploration strategy for Mars. Exploring the new frontiers, have conducted missions like this in the past. It's not necessarily new to the human race. It's just a matter of, do we have the will and the wherewithal to actually conduct those types of missions. So we know we can do it. We have historical precedents. It's just a matter of getting on with it and actually doing it, hopefully. This is the design reference architecture. I want to use this to kind of walk you through the mission sequence. And we begin it with what we call a split sprint approach. We pre-deploy cargo to the surface of Mars ahead of the crew in order to help reduce the risk and also enable some other architectural strategies. So we see here some heavy lift launches of vehicles to low Earth orbit, use automated rendezvous and docking of the systems in Earth orbit, trying to minimize the complexity of assembly. Get those vehicles checked out in Earth orbit and then send them on low energy transfers to Mars. Take about a year to get to Mars. And when they get to Mars, we use aero capture using the atmosphere of Mars to slow down and capture into Mars orbit. We land one of the vehicles to the surface of Mars. And that is actually the ascent vehicle. And we produce propellants from the atmosphere of Mars. Extract the oxygen, produce oxygen for ascent, also produce some of the life support equipment, life support consumables. So that allows us to not only reduce the mass, but also some of the size of the vehicles. And we do that before we send the crew. So we know that propellant is there and it's produced before the crew ever leaves Earth orbit. About 26 months later, we then launch the crew elements, launch those in low Earth orbit, again rendezvous and docking to get them checked out, and then transfer the crew to Earth orbit and then out to Mars, again in one of these fast transits to Mars. We chose, in order to reduce the total energy requirements, plus in order to maximize the exploration capability, this long stay approach, staying at the planet for about 500 days. Once they get to Mars, they rendezvous with their habitat lander. They're going to be deconditioned. They've been traveling through space for about 6 months. We'll do our best to get them conditioned as best we can to get to the surface, but they will be deconditioned, so we land them in the habitat lander. Also for Mars entry and descent and landing, you're flying through an atmosphere. You don't have abort capabilities like you do, like we typically talk about for lunar missions, where we land in an ascent vehicle to board back off. Since you're flying through the atmosphere, you don't have that capability, and so the strategy becomes one of abort to the surface. So the crew lands in vicinity of the ascent vehicle, in their habitat vehicle, where they can then recondition themselves to start the exploration strategy. And they explore Mars for about 500 days, transfer to the other vehicle, ascend to Mars orbit, where they've rendezvoused with that transfer vehicle that's been waiting in Mars orbit while they're exploring the surface. And then again, 180-day transits back to Earth for direct Earth entry into the mission, 30 months later. So total mission duration for the crew is about 30 months long, which is a significant period of time. So if you take that general mission approach, and that's, again, design reference architecture, it's built upon a foundation of a lot of other studies. And you see up here in the next chart, some of the key challenges that we have found and we continue to find through these architecture studies of what are some of the key things that are required from a human exploration of Mars perspective. Heavy lift, we see as one of those critical elements. So the SLS that Charlie talked about, evolving to a capability of about 130 tons will enable this type of an architecture. Each time, even when we dial in all those technologies, Charlie talked about if we went with today's technologies, it would be 8 to 12 times the mass of what we think today in terms of space stations. Even dialing in all those technologies, it's going to be about 2 to 3 times a massive space station every time we send a crew to Mars. So heavy lift and being able to have robust heavy lift capability is really one of those enabling elements. But that's also large volume. being able to launch large volumes is also key. I talked about entry, descent, and landing. Today, our capability is limited to about 1 metric ton of landed capability, landed payload on Mars. To do this type of approach, we're going to have to get to at least 20 tons. Our preferred approach is to get to about 40 tons of landed mass, per usable mass on the surface of Mars. So entry, descent, and landing, new technologies and new techniques to serve that is really critical. Human health and performance, I'm not going to talk too much about that. Dr. John Charles will discuss that in a minute to go into some of the details. And you also hear some more discussion on that in panel 3 later in this conference. Cryogenic propulsion, concepts like oxygen, methane type of engines, again, compatible with the in-situ resources that we want to produce on Mars are critical. So throttleability, long life reliability systems. Being able to extract oxygen out of the atmosphere, we found that to be very, very useful from a total leverage and total exploration architecture enabling capability. So extracting oxygen out of the atmosphere is key. Advanced in-space propulsion is key. Ben Donahue will talk about that a little bit more. You know, within the agency, yeah, we're rocket fire and smoke type of people because it's key for these exploration architectures. Really maximizing our propulsion capabilities, launch vehicle capabilities is important. But right now we have various different concepts still in play that we're continuing to look at. Advanced chemical propulsion, nuclear thermal, nuclear electric. You know, the question came up about VASMIR, the VASMIR engine. We're continuing to investigate it. It is, you know, electric propulsion type concept, nuclear electric. So we're continuing to investigate it in terms of its capabilities and use. And if we have time, we can go into a little bit more in terms of that technology in the question and answer session if we need to. Reliability and maintainability is another one of those key challenges. As we talked about, no matter how you slice it and dice it, you know, human missions to Mars are 18 to 30 months long. And so having the capability to have reliable systems, being able to repair systems, the crew is not going to have anytime logistics. As you see, the opportunities going to Mars are very limited. So the crew needs to take all their capabilities and systems with them to be able to repair things should they break. So advanced logistics and reliability and maintainability are important. Cryogenic fluid management, consistent with that advanced propulsion concept, is important. Being able to store oxygen, hydrogen, methane, and perhaps xenon, things like that for long periods of time, 900, 1,200 days in space with as low a boil-off as we can is important. Advanced operations, new concepts of the human exploration of Mars will require us to look at the problem differently. We're not going to be able to see every bit of data real time coming down from these missions. We're going to have communications delays that we're going to have to deal with. We are not going to have anytime logistics, as I mentioned earlier. So once the crew gets out, few days out from Earth, they're committed to the long mission. There are no really good abort options. Any abort options are still long in duration. New operational concepts, the way we approach the problem from an operational perspective and ingraining that into our philosophy is going to be important. Surface power, you know, Mars is kind of a harsh environment, and so advanced in-space propulsion. Right now our concept is a nuclear fission reactor, about 30 kilowatts total power, consistent with what we need for our ISRU producing the propellants, but also while the crew is there is critical. So advanced power, keeping the crew healthy and maintaining them. Science, we're there to explore. So providing exploration mobility, where we land is going to be in a safe location. We're not going to land in a very dangerous location. Generally those safe locations aren't necessarily geologically interesting right at the location. So enabling the crew to be able to do long-range exploration and explore the geologically interesting sites is going to be key. And Dr. Beatty will talk about that a little bit more in his discussion about Mars and what we have today. And when you look at that, as Charlie talked about, that's, you know, in the grand scheme, that's a lot to bite off in one chunk. And so we don't view the strategy as straight to Mars, but it's an incremental approach. And you look at all those technologies that are required, from a human exploration of Mars perspective, and you map, what we're doing is we map those back to other destinations and say, okay, which technologies are required for the various destinations, and which of those technologies make most sense to demonstrate and prove some of their capabilities. So you'll see within near space, for instance, space stations, a lot we can learn in terms of the human health and performance, a lot of the operational aspects of maintaining systems for long periods of time, a lot of those gravity phenomenon type of issues. We'll talk about that as the conference goes on. But it's an incremental approach as we're looking at it. And this is another slice of how you can look at it, which Charlie talked about. The path that we go to Mars is still evolving. This is a snapshot of what came out of the Human Exploration Framework team late last fall. And it's an incremental approach, looking at various different destinations. What we might do in low Earth orbit, what we might do in higher Earth orbit, like geostationary orbit, repairing satellites, things like that. How lunar missions fit in terms of proving some of our capabilities and systems. All the way out to perhaps near Earth objects. Exploring asteroids can serve as a good vital test run of an eventual Mars mission. So it's an incremental approach as we look at the systems and understand their capabilities in order to tie this framework together. So we don't just focus on necessarily on one destination by itself, but really understand how all the destinations drive some fundamental key capabilities that all work together to establish and achieve our goals as we go along. If you look at another way of slicing that, if you look at it from a human health and an exploration perspective of Moon versus Mars, we want to get to the planetary surfaces. So there are some common capabilities and needs as you look across that spectrum. The Moon can serve as a good formulation in terms of really understanding the surface operations, testing the operational procedures, understanding human health and reduced gravity in a 1/6 gravity environment as an analog for Mars missions. Proving a lot of our systems and capabilities. Near-Earth asteroids, on the other hand, can serve as that test bed for a lot of in-space transportation elements. Getting crews to remote distances as quickly as we can, exploring those destinations and getting them back. So the transportation elements, the in-space habitation systems, life support, those sorts of things. There's a common intersection in the middle between those where we need some capabilities that are common between all those destinations. Heavy lift, in order, efficient, robust capability of launching systems in space, getting crews to low Earth orbit to start those missions off, and then at the end of the mission, high-speed return, to return the crew back to Earth. And if you do things right, and think systematically of how Moon can play in those lunar systems, how does a lunar rover compare to a Mars rover, or is it evolvable to a Mars rover, a lunar habitat evolving to a Mars habitat? Keeping those synergistic capabilities in mind is kind of the heart of this capability framework that we're continuing to evolve and establish. So if we all put our minds together and think hard about how we can drive those commonalities, hopefully we can accomplish multiple objectives, multiple destinations with very similar systems and not have to restart every time we go. And from a testing and an evolutionary strategy, it's again an incremental approach. Space station, as I mentioned earlier, is a critical venue for a long-term demonstration of how things operate in zero-gravity environments, so life support system, habitation systems, maintenance and repair like we talked about earlier. Mentioned the Moon and how it can serve in near-Earth asteroids, but we shouldn't also forget the robotic systems. Paving the robotic systems always pave the way. I showed you earlier some historical snapshot of human exploration of long duration in the age of exploration. They didn't know much about. They didn't even know anything about where they were going. Robotic systems are providing a wealth of information, so we will know a lot more about the destinations that we want to explore before we ever send the humans. So those robotic systems, proving some of those technologies, gathering that critical data before the humans actually depart is really key, and that's part of the overall exploration strategy. So that gives you a snapshot of some of the challenges, some of the key enabling systems that we need in order to explore humans with Mars.